This is the review session for our practice exam. We'll go ahead, and so that's pretty much going to take up all the time today, just going over the practice exam. I'm going to go over all the questions, and I'll tell you, and I'll be able to tell you where in this exam this practice exam differs from your actual exam. So let's go ahead and start. First off, there will be 105 points on your exam. I just didn't happen to total them up. 35 points will be dedicated towards coding. The rest, all of the other 70, will be there'll be points that you can gain by on theory questions. Okay, second page. I will add string functions and map functions and trees functions, although you'll not need to use any of the functions for trees in here. But I will put the relevant functions for maps, like put, get, contains key, contains value. You really don't even need contains value. All right, so first page of content. This page over here, this is going to be exactly the same format as on the actual exam, and if I get my way, this will also be on the final exam as well. Give for each of the following questions, indicate which data structure is best suited to handle each scenario. Either an array list, a linked list, a stack, a queue, a tree, a priority queue, a set, or a map. So you know, you just answer. The only difference is that on the actual exam, I'll have a sentence here that says you can justify whatever your answer is, right? That's my difference on the actual exam. So, and that will help you if you need to turn a wrong answer into a right answer. So let's start with the first question. You need to model which patients should be seen next at a hospital. Patients should be seen in as close to order of arrival, but patients in a more severe situation should be seen first. So what data structure do you use to model this? Yes? You use a priority queue, right? Because it's a queue, people should be waiting, they should be seen. If I've been waiting the longest, I should be seen first, unless, of course, somebody has a worse injury than me, so they should be able to cut in line, right? That's kind of the way a priority queue works. Next question. A router needs to hold packets in a buffer and deal with them in the order that they appear. What data structure is that?
Queue.
That is a queue. Why is it a queue?
Because the first one to clean is also the first one to come out.
Yep, because with the buffer, and the way we're dealing them with we're dealing with stuff in the order they appear, that means the first thing we get, that's the first thing that we deal with, and therefore the first thing that goes out of the data structure. First in, first out for a queue. Anytime that you're dealing with information where you get information in and then you remove it in the order that it appears, that's a queue. Third question, you need to model a hierarchy. That's a tree. Yep. Trees are the hierarchical data structure. 4, you need a data structure to hold your previous decisions in case you need to backtrack. That is a stack. And so now, a very common wrong answer that we get, by the way, recursion. Recursion is not a data structure. It is a technique which takes advantage of a stack and a runtime stack, but it is not a data structure. Recursion is not a data structure. Right? Common wrong answer from people who've scored very poorly on their exams. If I see recursion there, it's generally not a good sign. All right, so the next two pages are combined into a 10-point question on the actual exam, and the format for that is that I give you a tree, and then I ask, okay, here's a tree. I've labeled the nodes, and so A is B's what? C is D's what? You know, those kind of questions. Then I say, if you change these nodes, right, is it now complete? Right, I make those kind of questions there. So let's go through this. So the node at the top of the tree is called what? It is the root. The links from a node to a successor are called what? Branches. Yep. Or links. Not a leaf. Not a leaf. a link from a node to its successors are called what? You can call it branches or links, right? Even though I just use links because everybody knows what a link is.
It's not child, right? Branch?
Not child.
It's like C and D too. The end is C's and D.
Yeah, kind of.
Branch, right?
Yeah, branch. So a predecessor of the tree is called what? In this case, predecessor, nobody actually refers to it as a predecessor. Everybody calls it parent.
Or grandparent.
Parent. An ancestor is a more generalized term. A grandparent would be, your parent's parent. Now, you could use ancestor or grandparent so long as grandparent is accurate for it, right?
The answer is parent for D.
Yeah.
For C.
C is parent. D, nodes that have the same parent are what?
Siblings.
They're siblings, yeah.
Oh, it's the
I don't know if that. I just kind of like guessed that.
Yeah, siblings, right? If so,
should not be.
I mean, come on, take a stab at this and guess the terminology for this, okay? Come on. Ridiculous. I mean, it could be, but not. I mean, this is actually, so we've got A and B. So what is B to A?
Uncle.
Uncle.
Yeah.
That's, and you care about that in your red black tree because it's easier than saying your parent's sibling. So it's way easier than saying your parent's sibling, except you can use one word that everybody understands. All right, so now this next question, which kind of looks out of place here, but describe without using code how to calculate the height of a tree recursively. So first off, what is the height of the tree I just drew on the board? It's 3, right? Because there's 3 nodes in the maximum path in the biggest path from the root to the child. 3. Okay. If I were to make, if I were to do this, right? That's a height of 4. That's a height of 4. Right? Now, what's the height of a tree? How can we? Now, you may not remember, but I did describe at the very, very beginning of the tree chapter I did describe how to calculate the height. That height is a recursive definition. Yes.
You do like with code I know how to do it, but I don't know if I have to describe. It's like 1 plus as long as the next does not equal null, root dot next does not equal null. 1 plus same.
Well, the nice thing is that if you don't have code, if you're not using code, you can be a bit more ambiguous about your statements.
Oh, okay.
So,
Like set a base case and then do 1
right,
plus next case.
yeah. So here it's fairly straightforward, right? My height is 1 plus the height of my biggest subtree. That's basically the recursive definition. My height is 1 plus the height of my biggest subtree, right? If I were to describe it in code, it would be, check first if root is null. If root is null, what's the height of the tree? 0, right? Otherwise, get the height of my left subtree, get the height of my right subtree. Here it's 3 and 1, right? And then get the bigger of the two. By the way, in terms of code, is there a function that exists that allows you to, if given 2 numbers, will give you the bigger of 2 numbers? Yeah. Anybody remember what it is? Because the Newton section failed me on this one. So there is a max function. It lives in math.max. And it takes in 2 arguments, right? And it will return the bigger of those 2 arguments to you. So it's pretty nice because now you don't have to write an if statement, an if-else statement to say which one is the biggest one, right? So math.max is great. So you ask which is the bigger of your left and right tree. And so my height is the bigger, is 1 plus that, right? So what's my height? Well, it's 1 plus the height of whatever's bigger, my left or right. Oh, my right tree is 1. My left tree's height is, it's 1 or whatever this is. Well, 1 plus whatever this is. And this guy is 1, so this guy's height is 2. So this guy's height is 3. So this guy's height is the bigger of 3 or 1 plus 1. So that would be 4. Make sense to everybody? How it's recursive So the next question, draw each of the following types of the tree, binary tree. Use a different example for each possible, for each tree, because, and the reason I specify that is that I didn't want somebody to just, be lazy on their exam and say, and then draw this for each answer, because this is both a full, a complete, and a perfect tree. So,
But we can use one.
but you could use it for one, yeah. So, okay. Why is this a full tree, by the way? Why is this full?
Because you can either have two or none.
Yeah, because every node has 2 or no children. By the way, I have no idea whether this, an empty tree, is full. I'm inclined to believe it is, because every node has 2 children or no children. But
So leave them blank.
only if you put this space intentionally left blank, I guess.
Oh, so I can use the one circle for one of them.
I suppose you could. But anyway, but I mean, all right. So anyway, all right. So next, let's go. So let's go ahead. So this is a full tree. This is not full. Neither is this, because I still have one child, because I still only have one child. On the other hand, this is a full tree, right? If I add one over here, it's no longer full. But if I add another over here, it's full. By the way, it's also perfect, right? Now, what does perfect mean? So going on to perfect, which is C, right? I'm skipping B and going on to C. I'll come back to B in a bit. Yeah.
Does everything have to have,
So perfect says if this is height h, then it has 2 to the h minus 1 nodes, right? That's the definition of it, which doesn't tell you much, right? But honestly, it looks pretty straightforward. Essentially, if it's of height h, then every possible spot where a node is filled. Is another way of putting it. So this is height 3. There's 7 nodes in there. 2 to the third minus 1. That's 7. 7 nodes here. So a perfect node of height 4 has 15 nodes, right? Because we're adding 8 more, because that's how many children we can possibly add on. And so we'll have 15 children. Sorry, 15 nodes in here. I'd have to draw 2 children for every one of these to make it a perfect tree of height 5, which would be 31 nodes. I'm not going to do so because I'm lazy, and I don't have the time. All right, so let's go ahead and erase a bit of this. So this is an example of a complete tree. Now, a complete tree is perfect for the topmost layer. See how this topmost height is still a perfect tree, right? Everybody see that? But the bottom layer, the bottom level, has a rule unto itself, a special rule, which says that the nodes in this bottom level need to be filled in from left to right, without any gaps. Okay? So this is a complete tree. This, however, is not, because there's a gap here, right? This is a complete tree because it's filled in from left to right. Over here, not complete because there's a gap.
Still not.
Still not complete. Now it's a complete tree. Not complete because the upper level is no longer perfect. Right? Make sense to everybody? It's got to be filled in left to right. Now the reason we do this is because, the reason we care is because it's very easy to map a complete tree to an array. Right? This is index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So those map to each of the specific indexes. So it makes it very easy to do that. Yes?
when you ask us to draw this, do we have to put any kind of value on the nodes? Or
No.
just really
You could just draw the shape and it would work. That's what I was really caring about here. On the tree, on the exam, I'm pretty explicit about what you need to do, and I'll tell you. And there's no ambiguity as to what you need to do on the exam. So okay. All right. And no, because I've been asked this question. No, I will not have you write a method that will test whether or not a tree is complete. That seems a bit hard, so I'm not going to do that. So, I mean, not impossible because it's a definition. All right. So now tree operations. So let me go ahead and just show you. So there, so it's caught in the video. Boom, tree operations 2. So here, this is exactly as it will appear on the exam. The only difference is the numbers that are going to be used. Okay, the only difference are the specific numbers. Now it's pretty easy for you to maybe make a minor mistake, like instead of inserting 42 first, you accidentally insert 24 first. Right? You accidentally transpose the numbers. If you do that and we see that on the exam, we're just going to kind of roll with it, mark you a point off, and just and whatever that happened, minor mistake. If, however, you draw a tree, you draw some weird tree where basically the values are all over the place and it does not resemble a binary search tree at all, or you've got something and now has 3 children. Yeah, so we're going to have mistake. That's going to be issues. So I've never actually had a student do that. Please don't be the first one. But that's just an example. Most students, pretty much every student gets this right. I've only really seen students get it wrong when they really don't know how binary search trees work at all. And this question was like the least of their problems. Yes.
So far, what did you say was on the exam?
So
Just 5 or just 8?
and that question's going to, well, this map's pretty close to what's on the exam.
Oh, okay, so just there.
Basically everything on here is on the exam. Okay, so this question is a direct map. So this one, basically, this question has a direct analog. It's just the same question, but with different numbers plugged in, right? So how do you solve this? Well, we start by inserting 42, right? And then 10, and then what's the next one? 50? 50, so that goes to the right because it's greater. 12, 17, 80. 80? 80. Okay.
Negative 12.
100,
96.
Are you really computing that?
96.
105.
105.
86.
86. So greater than 80.
Left.
Yeah. Left. 6. 72. I wasn't actually working. I was actually just working off memory for all the other ones, wasn't it? Okay, 72. Any others?
No, that's it.
That was it. Negative 12. Yeah. Yeah. As I said, if you make so that's not something you need to worry about. Now, yeah.
What about duplicate values at all?
No.
Okay.
I don't think so. And if you do, just write how you handle it.
Okay.
I'll take his word for it.
Right.
So just put it in.
What's the general rule for
For putting a number in the tree.
Yeah.
So the way it works is that if it's less than, you go to the right. If it's greater than, if it's less than, you go to the left. If it's greater than, you go to the right. And you keep doing that until you hit an empty spot. That's the rule, right? Okay. So the next question on the exam that comes after this will actually be the traversal question. Right, so the next question on the exam is not the delete question, but the traversal question. That will go, but we'll get to that next. So when you draw your tree, the next thing I immediately ask you to do will be to do a pre-order traversal and a post-order traversal. Okay, which we'll get to in a bit. But first, we're going to go ahead and do the delete operations. Okay. So the delete operations using the previous answers. Yes.
For this, we have to show all 4 deletions, like writing out the tree 4 times. We just draw the final tree.
You could draw the final tree, but it's safer if you draw it out 4 times. But in this one, on the actual exam, on your deletion problem, I will give you the tree. It won't be as big as this one. I will give you the tree, and I'll say, show what the tree looks like after you delete these items from it. And I'll give you 3 deletions as opposed to 4. Right? It can give you more stuff on the practice exam because it should be harder. All right, using the previous answer, draw what happens when you group the following. 42. So 42, right? You have 3 cases. We have 3 cases when it comes to deletion, right? What are your cases? You have 2 children, you have 1 child, or you have no child. No child or 1 child, that's pretty easy. 2 children is the hard one, right? So what we do for that is that we find the next in order predecessor, right? The smallest thing, the biggest thing thing that's smaller than me. The biggest thing that's smaller than me. So that means I go one to the left, all the way to the right to find that. That'll be the biggest thing in my left subtree. So I find 17, right? Now 17 replaces me, and then I delete 17 from my left subtree. Okay. Now 17 has no child. So just do that and you're done. Right? Now what if, on the other hand, if 17 did have a child? In that case, we'd have 12 adopt that child. Okay? Okay. Now, what do we need to do for deleting 12? 12 is fairly straightforward. It's a leaf node, so we just remove it. Now we need to delete 17, which is the root. It had, yes?
What if something had 2 children? Though, so the whole thing just.
So right, excellent question. What if 17 had 2 children? And the answer is, we wouldn't be deleting 17. Because there'd be something bigger than 17.
Oh yeah.
You're always guaranteed that this node is not going to have 2 children.
Yeah.
Because if it did, you'd have one more to the right to go. So it's an excellent question.
Yeah, if I saw that on a paper, I probably would have done that.
So 12, so sorry, let's go ahead and delete 10. So not 17, right? We delete 17 to find the biggest thing in my left subtree, so go one to the left, all the way to the right, which is nowhere, right? We can't go anywhere further there. So we need to replace 17 with 10 and then delete 10. So how do I delete 10 since it has since it has a parent? Sorry, since it has a child? We simply have our parent adopt the child. Yeah, I am the epitome of grace and elegance. I know. So now to delete 96. We look for 96. We find it. It has 1 child, and it has its parent. So adopt. Yeah. So its parent adopts it. Yes.
You could also just shift the 50 to the top, right? Like you can, instead of shifting from the.
You want to be consistent with your deletion operations. You always want to delete the. You could have, but if you're deleting the next in order predecessor, always get the next. Sorry, if you're getting the next in order predecessor, always get the next in order predecessor. If you want to get the next in order successor, you can, right? But just be consistent, right? You may look at the tree and go, it's way easier to get the next in order successor. In which case, totally do that.
But like in this
That's
case,
what I did.
Yeah, that's
for
what
this case, it wouldn't really change anything, right? It would just
Right.
be 50s
Yeah,
at the top.
it would fit the child.
Yeah.
All right. So now let's go on to this one. So which of the following is a pre-order traversal of the tree? Which of these options? B. Do pre-order. In other words, do the root first, then handle the left, then handle the right. So to do that, so let's go ahead and do a pre-order traversal of this tree. Let me just go ahead and again, I want to make sure I'm capturing mostly this, so that there's the question on there. And now that's back
You're
to.
recording everything?
Yeah, I've also already uploaded last night's review of this and the noon review of this, so it's already online in case this one doesn't,
okay.
in case this one doesn't make it. So this is part of the reason I started doing the lectures or flip lectures, because otherwise I'd be doing 3 separate recordings for everything. I mean, it would work. Why not? But I don't know. I wanted to try doing something else and seeing if you guys would enjoy that. So seriously, what?
Hi, YouTube.
So let's go ahead and do a pre-order. Okay, pre-order traversal. So we start at 10. We handle 10 first, then we handle 10's left subtree, then its right subtree. Its left subtree is -12. For -12, we handle its left subtree, its right subtree, so we're done with -12. So 10's left subtree is done. Then we go to 50. We handle 50, then we handle 50's left subtree, which is nothing, then its right subtree. Then so we're at 80, we need to handle 80's 80, then handle its left subtree, then its right subtree. So 72 is the left subtree, handle 72. Handle its left subtree, its right subtree, we're done. We're done with 80's left subtree. Now we're into 100, handle 100's. Handle 100, handle 100's left subtree, which is 86. Then handle its right subtree, which is 105. So we're done with 100, we're done with 80, we're done with 50, we're done with 10, we're done with the whole thing. So that was 10, negative 12, 50, 80, 72, 100, 86, 105. So you'll be expected to do a pre-ordered traversal of whatever you draw, or whatever you end up drawing for your tree end question. So now, and of course, I'll also ask the corresponding question of which of the following is a post order, right? And you'll be expected to do a post order on the exam. So post order is which one?
What was the first one?
This is a pre-order.
The first one was a B?
It was B, yeah.
We do all the notes first and then
And then this is, so this one is C, which is post order. So to do a post order, we do left, then right, then ourselves.
And
So
this is based off the very first tree that you're gonna ask us to draw?
yeah, it will be explicit. I'm telling you what's going to be on the exam instead. On the exam, you'll see a question instead that says, use the tree use the tree you just drew to do the following, to give me the following, traversals.
Okay.
Right? They will say that on the exam instead. So let's do a post order this one. So we're at 10. We want to handle our left subtree, then our right subtree, then ourselves. So let's handle my left subtree. 12 says let me handle my left subtree blank, my right subtree blank, then I'll handle myself, negative 12. Okay? So 10 says my left subtree is handled, let me handle my right subtree. 50 says let me handle my left subtree blank, we're done with that, now handle my right subtree. 80 says let me handle my left subtree. 72 says let me handle my left subtree blank, right subtree blank, handle 72.
Wait, why did you skip 10, 50?
Because they all have children, we have to handle them. So now 80, so now we're going to do our left, so now we're in our right subtree. We go to 86, 86 says handle my left subtree, my right subtree, which are blank, so we don't do anything, then handle myself, so we
Oh,
do
so you
86.
use those ones.
So now 100 goes, says we're done with my left subtree, now we got to handle my right subtree. So we handle 105. Because 105 will say, let me handle my left, my right, now I handle 105. So now 100 says, oh great, I've done my left and my right subtree, so I'm done. And then 80 will go, great, I'm done with my left subtree and my right subtree, so I can finally handle myself. And 50 will go and say, I handled my left subtree, I did my right subtree, I'm done. And then 10 will go, great, I'm finally done with that huge right subtree, so I can finally handle myself, and then we're done with the whole thing. Yes?
So is there any particular significance to doing these orders? Like neither of them had like the numbers in the same order.
So-
Very new, right?
So they come up in the graph here. They come up in the graph theory, they also come in like if you're building a they're not just questions that are made up for the sake of being hard. All right, this page will almost exactly be the same on the exam as well. Heaps. So draw a min heap, meaning smallest thing is at the top. That forms after inserting the following integers, right? So here we're showing what happens if we insert one item at a time. We're not trying to turn an entire array into a heap. We're saying we're going to insert these items one at a time. Common misunderstanding there, and if you happen to have misunderstood that on the test, the practice exam, well, that's okay. I understand why that happened. And then this question over here will be almost the same. It will just be a slightly easier version. So, in fact, it will be super quick if you get the trick behind it. So anyway, so we're going to draw a mini heap that forms after inserting the following integers. 8 will be inserted first. And you can ignore the underlying array. That means that you don't really have to care about that array, that you don't have to draw the array. You just have to draw the tree structure that forms. All right, so we've got 8 as our first insertion for the heap. So 8, then what's next? Actually, let me just draw 8 without the circle. 8, 10. So 10 is heavier than 8, so it stays put. Then 50. 50 is heavier than 8, so it stays put. What's next? 20. 20 is heavier than 10, so it stays put. 1 is lighter than 10, so it swaps with 10. It bubbles up. Then 1 is lighter than 8, so it bobbles up. Right? So next, what's next? 4. 4 is lighter than 50, so it bubbles up. 4 is lighter than 50, so it bubbles up. But 4 is heavier than 1, so it stays put there.
3.
Then 3. 3 is lighter than 4, so it bubbles up. And then it's heavier than 1, so it stops bubbling up. Right? For a min heap, the heavier items sink, well, the lighter items float to the surface, where we can kind of just define height as the.
Need the bigger numbers?
Yep.
The smaller numbers?
We can just. Yep. Where we can define. It's generally easier to do that with a min heap. That's the easiest way to understand that. All right. If we were to, so let's go ahead and. So how does removal work, by the way? Now, the next question says remove 2 items. So there's only 1 item you can ever remove, right? So just before I move on and forget, by the way, when do people lose lots of points on this one? Because invariably this is the page where I see people just lose like 8 points and otherwise have a good exam. It's because they completely forget that a heap is not a binary search tree, which means that a heap always has to be complete. And the smallest item is always at the top. So if I see something that looks like this, 1, 3, 4, 8, like if I see something that looks like this, right, we just mark it wrong because it's not a complete tree, it's not a heap, right? Heap has to be a complete tree, especially for the purpose of the removal operation, because we remove only the root, and then you replace it with the last item in the tree, the last item in the heap. And that, by the way, that happens to be the only item that if you remove it, the tree maintains its complete property, right? If you were to have moved any other item up, the tree would have no longer been complete. The heap would have no longer been complete. So we move 4 up. However, we need to restore now. This guy's not the smallest thing in the heap, and the smallest thing in the heap needs to be at the top. So now let's check. 4 is not heavier than 8, but it is bigger, heavier than 3. So it is going to sync and swap with 3. Right? Now suppose 50 had been 2 instead. Let's just suppose for the sake of argument 50 had been 2 instead. At this point, 4 would also then swap with 2. Okay? Right? It just keeps swapping until it needs to stop. But let's go back to the original example. Okay? Yes?
Wouldn't 2 have already been swapped with 3 at that point?
Yep. It would have been. It would have been swapped with that at that point. So excellent point there. So that would have never happened. So, but I needed to have I needed an example of some kind. I think probably a better example would have been, in this case, 3.5, right? Swap with 4 with 3.5, right, at that point. Okay, but let's go back to the original example. So now we make another removal operation. So we remove 3 and replace it with the last item in the heap. So now this item is bigger than both of its children. So we swap with the smallest child, which happens to be 4. So this is the state of the heap after we do 2 removal operations.
There's no scenario in which the left side tree can be touched.
you actually pretty much reshuffle only a line. Whenever you do a deletion or an addition operation, you're only ever modifying a single line to the root or to the bottom. And as a result, that means that the operation will take log n time. Right? If we put in 1 over here, right, it's not going to affect everything in the heap. Right? The heap over here will be completely unaffected, and so will the heap that starts at here. Instead, all that is affected is this path. Right? All that could potentially be affected is that path. The path to the root. Do people want me to build another heap? Just on the fly? Okay. So give me reasonable numbers. So numbers between 1 and 100.
77.
So 77 is at the top. Okay, another number. 8. Okay, 8 is smaller, so we swap with 77. 8, 77. 21? 21, right? Next number? Negative 2. Keep me with positive numbers right now. I'll go with 2. No, I just don't want to accidentally leave off a negative. And then so 2 swap with 77, and 2 will swap with 8. Okay, another number. Let me go ahead and do 5. So 5 would swap with 8. Another number. Anyone? 66 would stay put. 10. 10 will swap with 21. All right. 3 will swap with 77. Then 3 would swap with 5.
How come it's on that side? Does it matter?
Why is it on that? Why do you think
Oh, you always start on the left side.
Because you always start on the left side because it needs to always be a complete tree, right? So the next, we always insert in the place where which would make it complete. What was that, 5? Yeah, 5. So the next item we insert, regardless of where it's going to go, is going to go over here. And once we fill up this layer, the next item would go here, right? Right. When I put here, here, right, and so on and so forth. And the next item is here. So let's go ahead and see how a removal operation would work at this point. Removing 2 would replace 2 with 77. Right? Because that's the last item to remove. We wouldn't replace it with this. The tree has to always be complete, so we remove the last thing in the heap. 77. 77 is bigger than both its children. So we swap 77 with 3, the lighter of the children, so that lighter one becomes the root. 77 is also bigger than both of its children now. We still swap it with the lighter of its children. And in this case, by the way, it was only happenstance that the left children were less. Could have easily been the other way around. For the heap, it doesn't matter that the left tree is 5, 77, 8, and the right is 10, 66, 21. They could easily just be transposed, and it would still be a heap. So let's go on to the next item in our list. All right, so this is another page that will be, so this one does double duty. This one is going to both be on your exam, pretty much like this, and it'll also be on your final exam, where it's worth 10 points. Now, since your final exam is worth a grand total of 25% of your grade, this means that if it's worth 10 points on your final exam, then this question is worth mastering this question for your final is worth a full 2.5% of your grade. Yeah, no pressure, right?
Like that.
I'm just trying to emphasize that don't slouch on this one and try to understand it. So the point of Huffman coding is basically we want to try to make files smaller, right? That's the overall objective. And the idea here is that we take a document and use just the symbols in the document to produce a tree that we can use to encode the message. Rather than using 8 bits per character, we can use less per character. We can, in fact, dynamically size it. the document that has the following symbols and frequencies. Okay. So the two mistakes I see from students who do this, by the way, are the two common mistakes I see for students is first they forget that that the first two items we DQ, the first item we DQ always goes on the left. The second item we DQ always goes on the right. So that's the first mistake. The second mistake is that they forget that after they build it, it's still a priority queue. So that when you reinsert an item in, the order, it needs to swap order around. So let's go ahead and make ourselves a priority queue out of this. So A is 50. So let's see, A 50, that probably is going over at the end. Actually, what's the smallest thing in there? That's X, 1. One instance of X, and L occurs 20 times, P occurs 40 times, A occurs 50 times, and then E occurs 60 times in this particular document that we read. Okay? So we use this to build our tree. So so basically, the algorithm is pretty straightforward. While there's more than one thing in here, we DQ the first two things, combine them, and reinsert it into the tree. So how does combining them work? Well, let's DQ this one. As I mentioned, the first thing we DQ goes on the left. The second thing we DQ goes on the right. Combine them, and we'll have a combined weight of 21. That makes sense to everybody?
Is that an L?
Yep.
You added them?
Sorry?
You added them, 20 of them?
Yep. 20, X occurred once. L occurred 20 times at a weight of 20. So since X was the first thing we DQ'd, it went on the left. L went on the right because it was the second thing we DQ'd. Now, we have to reinsert this into our priority queue. But it's a priority queue, so it needs to reorder. So even though we slap it in on the end, it cuts its way to the beginning, right? Because it has the smallest weight. So next, we DQ twice more. So we DQ twice more. So this will be on the left, and P will be on the right. It's L. Oh, it's a very badly drawn L. Okay. So now it has a combined weight of 61. So now we reinsert this back into the queue. Right, and I like this question because this node ends up both at the front and at the back. Right? Yes. Oh, sorry. So now we DQ again over here. So A gets DQ'd, then E gets DQ'd. For combined weight of 110. Right? So essentially we started a new tree here. Yes?
Can you backtrack a little bit to where you got 61?
We got 61 by DQing. We got 61 by DQing this node and this node over here that had a weight of 40, and combining them together into a single node. So
How are you picking the numbers, like for the symbols?
the symbols,
Randomly or?
well,
How come you pick X, L, and then P?
I gave them to you.
I know, but how come you picked them in that order?
Because that was the frequency. Right, the number associated, so the number associated is the frequency. Right, so I had 20, so what, I had 40 over here,
He was 60.
50 and 60. So 50 and 60, right? P had a 40,
Thank you.
and we had a combined rate of 21 over here, right? The order, we get these from the frequency I gave them. So you DQ this one on the left. You DQ, this one goes on the right. And so now they get combined into a new node with a combined weight of 21 plus 40. Gives us 61. So we insert that into there and it comes up and out at the end. Now we DQ twice more for 50 and 60. right? Because there's more than one thing still in this. So we DQ twice more, A, E. So it's 50 and 60, so it has a combined weight of 110. Now we reinsert 110 and we insert this node into priority queue. Now there's still more than one thing more than two things in this. Sorry, more than one thing in this. So we DQ twice and combine them. 61 was was the first thing out, so it goes on the left. This was on the right, so it goes on the right. So we have a combined weight of 171. Reinsert that into the queue. It's the only thing left. So this is our tree. Now it is possible, by the way, that you may have accidentally drawn something like this. Right? You get 110, A, and E, and you realize, wait a second, I accidentally put it on the left over here on my paper. And so you realize you have to do something weird like this, just simply because of how you drew it. Right? Notice I just drew it over here. Right? So that happens on an exam sometimes, so don't worry about that. Does everybody understand what I mean by that? Okay, right. So this is our tree. So now we label the edges, the left edges with zeros and the right edges with ones. Okay? All right. So now we can use this to encode or decode a message. Now the encoding and decoding. All right. So the encoding and the decoding, by the way, they're independent of each other. Oh, sorry, not the encoding. Drawing your tree and your encoding or decoding is independent. So even if you get the drawing of your tree wrong, we'll still run with that as your answer. Right? So long as you encode or decode properly according to your tree, you'll be able to get points. So we're encoding apple. Okay? So first thing we need to do is produce the bit combination for A. So A, we get to A by doing 1, 0. Then we need to do P, 0, 1. There's another P, so another 0, 1. L, 0, 0, 1. It's almost like I've done this a bunch of times. Then 1, 1. Or E.
Is there any spaces between the numbers?
No, I just simply put in the spaces to separate them and underline them just to separate them out to make it easier for me to read. And make sure I don't and to make it easier for you to see so it doesn't become like this horrible mess.
Zeros dip the left and one dip the right.
Yep.
Yeah.
So on the exam, I'll probably ask you to decode something on the other hand. So how would you decode, let's see, so what would this decode to?
Put spaces or
No, I just give you a full string. I'd give you a string, I'd give you something like this. So let's start at the top. So 0, 1. So you would go 0, you go to the left, 1, you go to the right, you get a P. Then we start from the next one. 1, so we're here, and then 1 again. So 0. 1, 0.
So you start at the top at 171.
Yep. Then we start again at the top. 0, go to the left, 0, go to the right, 1, go to the left. Sorry, 0, go to the left, 0, go to the left, 1, go to the right. L, 1, 1. So this comes out as pale. So on your exam, I will probably give you something to decode. It will, and I forget which one it is. It's either the word glove or it's a fruit. I don't know which one.
I know where I'm putting that.
So,
I'm just gonna guess love.
but that will be, that will give you a way to decode. But the decoding portion acts as a way to check to make sure your tree was right. Because if you decode gibberish, then you know that your tree, then you know your tree is wrong. So. Yes.
On the exam, if you were to encode something, rewrite it in bits of 4 like that.
Sorry? The bit before just happened to be coincidental. If you decode something or encode something, yeah, just make it easy for us to read, but I pretty much, when I code this page, I pretty much glance at it and go, yeah, that looks correct. I'm not super, it's super easy to miss a 1 or 0, so I just simply look, yeah, that looks about right, yeah.
If we start at 171 for the first key, how do you know if, like, should go left or right?
The 0 tells you to go, the way the branches are level.
Oh, it says 0, 1, so it's not.
So, right, 0, 1.
Yeah, you can't go any other way.
Right. So we get to the P, then we do 1, 0,
Yeah.
then we go 0, 0, 1, then 1, 1. So every time we hit one, hit a letter, we start at the top. Okay. All right. So that's that for the theory portion of this. Well, most of the theory portion. There's one more theory portion. Now we're going to go ahead and do the coding portion, which is actually, I find, to be fairly straightforward. So recursion only exists on the exam in the terms of, let's see. So recursion only exists on the exam in this case. Let's see. In the case for trees. So let me go ahead and delete what I've already written for the previous classes. Everybody can see it just fine? Okay. Make it bigger. All right. So here we go. So the first question is actually a question that I did ask my first semester I taught this class. So this is actually from the actual first exam I ever taught for this school, and then and I can pretty much say that there's a question like this. Let's see, as far as difficulty goes for like the final exam, you're gonna get something that's around this difficulty, with maybe one line more worth of complexity. Okay, so literally just one line more and complex for the final exam. So anyway, write a method which, given the root of a tree or subtree, computes and returns the number of nodes in that tree or subtree. You may not use the size method. Forget it even existed. So here, let's go ahead and write it. So let's go ahead and start. So what's the size of the tree if it's empty? If root equals null. And remember, root here, that's the local variable root. It's not this root. It's a root. It's a node. The node of a tree or a subtree, right? It's important to kind of just remember that. When we're talking about root, we're talking about a node. We're talking about this node over here, which has left subchild of unknown, left subchild of unknown, right subchild of unknown, and it may or may not have a parent. It may or may not have a parent. It doesn't know. It doesn't care. Okay. Okay. So if root is null, return 0. Let's see. If root is null, return 0. Great. So otherwise, we need to calculate, well, we've got the whole left subtree. We've got the right subtree. Calculate how big those are. Right? I'll figure out how big my left subtree is, figure out how big my right subtree is. And then I count as one thing, so I'll add 1 to it. So int left is equal to size tree root dot left. Int right is equal to size tree root dot right. Then return 1 plus left plus right. So the answer looks something like this. Doesn't have to be that. There's other ways. But that's essentially it. That's how you calculate the size of your left subtree and your right subtree. And then you add 1 to it because that's the total size.
So you're using recursion to figure out the height?
Yeah, and the size.
The size?
The size here. We're figuring out the size of my tree. Now, we can make this shorter, by the way. We can just simply simplify this to return 1 plus size tree root dot left, right? 1 plus the size of my left subtree, and add onto that the size of my right subtree. Okay. So that's that one. Now this one I'm particularly impressed with because, you know, it's targeting a definition in this. It's attacking a definition, right? It's asking, hey, can you write an algorithm that tells me whether a tree has this property or not, which is, you know, something I really like, and I really like kind of testing on an actual exam. So write a method which, given a tree, returns whether the tree is a full tree. So this is going to be slightly different, as you're going to see in a second, because of our base case, or rather one of our base cases, right? Because how do we know if a tree is full or not?
You either have 2 children or no children.
2 children or no children, right? 0 children or 2 children, right? So, first things, if tree is null, return who? Again, that was like, I don't know what we should return there, right? Should we return true or false? Is a completely empty tree a full tree? Yeah. So, I mean, yeah, sure. I mean, I wouldn't know. What?
Why is the node tree?
It's just the name.
Oh, okay. I just curious whether that's
Can we return maybe?
I mean, if this was capital B Boolean, you could return null. If it was capital B Boolean, you could return null. But I'm going to go with true. Although, interestingly enough, unless the whole tree is empty, this base case will never actually get hit. But so, anyway, but we'll put that in there just because we need something to put there. All right, so if I've got so how do I know if this tree is full? Well, if I have no children, if tree dot left is null, and my right tree is null, so that means I have no children. Right? I have no children. So what does that? So that means that I can return true. This is a full tree because I have no children. On the other hand, if I have a left if I have a left subtree, but not a right child, right? Oh my! Return false. And the same goes for the opposite case, right? If tree.left is null, but tree.right exists, that's also false. So great. 0 children, a right child, a left child, but not the other one, right? Those are base cases. So the only case that's left is, what if I have 2 children? Well, I'm full, but I don't know about my children. So, in that case, I have to check to make sure if they're full. Return is full, tree.left, and is full, tree.right.
How come you have to do both
For these? Because I have to check both scenarios. If I have one but not the other.
Is there a way of combining both? To, like,
You have to like else.
Can you just do, like, both of them are full? If both of them aren't null, then go into the checking both subtrees. And if there's anything else other than them both being null, it's very false.
I don't know.
Just make it like an if else.
Like,
Okay, so do I have to make this an if-else statement? No.
Just to like simplify it, would that make it easy?
I mean, I could, but I was being quick. I mean, I could put else's in front of each of these, but there's no need because they are all return statements. So, but I should because that's.
But do you need that first statement there?
I actually, kind of. If the very first node you pass in is null, then you kind of need it.
So this would work recursion?
Yes. What? Well, okay, so base case, right? I have no children, or I can immediately detect I'm not full. So then I ask, is my left subtree full, and is my right subtree full, right? If my left,
Okay, so you basically just treat the left child and the right child as
their own trees.
root node.
Yeah, that's what it means to be. That's exactly what it means to solve it recursively. And solving any problem I give you for trees will be solved using recursion.
So this is how you code that answer that we gave earlier in the packet.
Yeah, you would, but that one has to deal with getting the height, right? You would
Oh,
solve.
yeah.
Yeah, so anything that I give you, it's going to be expected that the way you can solve it is to do it recursively. You don't have to solve it recursively. However, I have yet to see I have only seen one student do problems like these without using recursion, and he used a stack. So, I mean, it's just making it hard. It's doing recursion, but just making it harder on yourself. All right. So now onto the hash table question. Yes. So the hash table question, by the way, so I've already went over this extra practice question, by the way. So you'll have 2 tree questions. So write a method which returns what characters occur in a string and how many times each occurs. Right? This is very similar to the one you took in your. This is very similar to the one you took for your exam, for your quiz, right? So this is the kind of question you'll be able to expect. So in other words, if the string you pass in is apple, I should expect to get back A1, P2, L1, E1. If I pass in banana, I should get B1, A3, N2. Right? Because A occurs 3 times a banana, B occurs once, N occurs twice, I think. Right? I mean, the issue with spelling banana is that you can start spelling banana, but stopping spelling it is a bit of an issue. So, write a method which returns what characters occur in a string and how many times each occurs. So here, first thing we need to do is create our map. If you can just bear with me for a bit longer. So if we can make so first we want to make our hash map. Not mad. I just want you to. I just find it hard to think, and I instinctively try to listen into everybody else's conversation. So it makes it a bit hard to code and talk and listen at the same time. So map character integer to hash map. All right. So first off, we create our map, and now we have to iterate through our string. Now, we could iterate through our string like this, right? This is the way that you've been taught to do it. Int I is equal to 0. And the way I said that derisively obviously implies that it's the wrong way to do it. But int I is equal to 0, I is less than word.length, it's just the longer way to do it. And you gotta remember, wait, word is a string, so the length needs parentheses. Ugh. So I plus plus, right? And then you would say, car letter is equal to word dot car. Wait, does at have a capital A? I don't know. Right? So much stuff. Easier if you do it like this, especially since you don't care about the indices. Car for every letter in Word, and the only thing I have to do over here is to do to-car array to turn it into an array of characters. And so now I can iterate through that. So for every letter in the word, if map dot contains key, right? Have I seen this letter yet? So if I've seen the letter, then int occurrences is equal to map dot get letter. This will get me how many times I've seen the letter, right? So if I've seen the letter, get how many times I've seen that letter. And now map dot put letter occurrences plus 1. So we increase the amount of times I've seen this by 1. Make sense? Otherwise, if I haven't seen it, well, I've just seen it for the first time, map.put letter, and now I've seen it once. Return map. Notice that basically the meat of this, the part where you're actually doing problem solving, doesn't really involve too much. It checks, have I seen this key? It's the way Java handles contains. There's a contains key and there's a contains value. Right. The contains key says, have I seen this character before? A contains value would be, have I seen this, is this integer in my values?
So there's very similar code with the word count.
Yep. Mm-hmm. So, okay, let's go on to the final questions of analysis. So in the actual exam, they're both going to be worth 5 points. So the first one will cover hash tables and the second one will cover trees. So for question 21, what are collisions in hash tables? How do they occur and how are they handled? So what are collisions? Yeah, not when they get the same hash code. That's pretty close. When you get two values, so when you get two keys and they get mapped to the same index, right? When they end up at the same, when they want to occupy the same index, right? Because every item should technically try to have a different hash code, right? But when you get basically two values that want to end up in the same index of your hash table, that's when you get a collision, right? And that happens because our set of it's because the set of all possible keys, which is infinite, is bigger than our storage space. All right? So, so there's two ways to get around to handle that. So there's open addressing and then there's chaining. Well, actually, there's a lot more ways to handle it, but the two ways we've learned. There's, for instance, cuckoo hashing, which simply says that, I'm going to paraphrase here, and I may be completely wrong, but the way cuckoo hashing handles collisions is that if somebody's taken your spot, right, you get a collision because somebody's taken your spot, you kick that sucker out of your spot and tell them to go and find a new spot. Yes? So I'll get that. I'll get into that. Okay. So, excellent question. I'll get into that. So, why do they occur and how are they handled? So how do we handle them? Realistically, the way we handle them is with open addressing, right? That's saying if my spot is taken, I'm going to look for the next available spot, right? So how does that work? Well, the next available spot, right, I'll just say, oh, if I want to go into index I, but that's taken, I'll take I plus 1, or I'll take I plus 2, or I'll take I plus 3 if each of those are taken in turn. So, now, and that's called linear that's called doing open addressing with linear probing. The other way we learned about was chaining, which says rather than each index being able to hold a single entry, we instead hold a linked list, and so we can put a link. So we can put an item into the linked list if there's a collision. If you're the first item there, you make the linked list, add it to it. If there's a linked list already there, you just simply add on to the end of it. So it's very easy to resolve collisions with chaining. Now, you asked, at what point does it no longer have O of n time?
Yeah,
Well, what-
actually, there's actually another question.
Okay, so when would it be constant time? When it basically if we let the hash table get completely filled up, or if we had a terrible hashing function. So like if my hash function was key, so let's say my hashing function was h of key is equal to 0. So in other words, every key mapped to 0. That's a hashing function. Hashing functions are easy to write. Good hashing functions are really, really hard to write.
But is the hashing function also generating the hash code in constant time?
So the hashing function is what generates the hashing. Yes. We assume that the hash code generates it in constant time. Where that's based on that basically you're given an item and you can generate something in constant time. And really, these things do work fairly quickly. Like, do I have? Sudo. No, I don't have MD5. Check. Interesting. I don't really have a tool on here, but do I have SHA? Hash a lot. So, so these hashing algorithms, they're meant to be quick. Is essentially in terms of like you can chug through a pretty large file pretty quickly to generate the hash code. So the objective is that if we're using it for a hash table, it will take constant time to do it. So the hashing function itself, the collisions are what would cause anything to be O of n time, and either by having a bad hashing function or to have something, or to have something that really impedes that. Like if we have, look, the analogy I used in the video that I uploaded is that, imagine you've got a parking deck, right? Did you see that video? Right, okay. Yeah, imagine you've got a parking deck. If it's all the way full, it takes forever to find a spot. However, if half the spots are open, it takes a very quick, half the spots are open, so it's super easy to find a spot. So collisions are pretty quick to resolve. If you keep it low.
Is that a number sort of like that determines,
Yeah, there's a formula for it, right? I think I went over that in the video. There's a formula that Knuth figured out that said, hey, if you use open addressing with linear probing, then this is the expected amount of collisions, and it's independent of n. It just depends on how full your hash table is.
well, in the video, they sort of use 75% full before reallocating.
Yeah.
I'm asking, like, is 75% like, how is that? Is that just a randomly determined number? Is that indeterminate?
If a hash table is 75% full, then using open addressing with linear probing, then the expected amount of collisions or expected number of probes is 2.5. In other words, we're going to get, in other words, when you're inserting, you're expected to collide with, you're expected to first check if the initial state is the initial thing empty. If it's not, check your next one. And if that's not empty, check your third one, and by that point, you're expected to have found an empty spot. That's expected. So, however, there's not a guarantee, right? It's completely possible that actually an insertion could be O of n, and I went over that in one of the videos where basically I showed that basically we could get a bunch of collisions into that a bunch of things could end up in just a few of the indices. And that's a case where it would be O of n time. Okay. So what's the worst case runtime of insertion and deletion algorithms for binary search trees and why? O of n. And that's basically because in a balanced binary search tree, you'd expect basically going down a single branch will eliminate half your search space that you need to consider. All right, so it is pretty close to the time to go, so you guys are free.